Hi everyone, this is Mrs. Snook with section 2.5, the fundamental theorem of algebra. Our objectives today is to use the fundamental theorem of algebra to determine the number of zeros in a polynomial function, so how many zeros you have. We're then going to find all of the zeros in a polynomial function, including complex zeros. You can find the conjugate parts of complex zeros and find zeros of polynomials by factoring. The fundamental theorem of algebra says that any polynomial has roots that you can list as linear factors. So here's your factors: x minus r1, x minus r2, x minus r3. So to any polynomial you can write as linear factors that are just multiplied together. And your roots are the r1, the r2, and the r3. It also says that the number of roots you have is the same as the degree of the polynomial. So if I give you a polynomial that's a fourth degree, you should have 4 roots. A third degree polynomial will have 3 roots. Now, some of these roots can be complex, and some can be real, or we can have a combination. We can have all real, we can have all complex, and so forth. Let's take a look at examples of zeros of polynomial functions. So here's a first degree polynomial function, has exactly 1 0. And here's an example, x equals 2. That's 1 0. Now if I was to write that as a linear factor, I would say x minus 2 equals 0. And then also count multiplicity. So a second degree polynomial has exactly 2 zeros. And here's an example of x equals 3 and x equals 3. Those are 2 zeros. They're in the same place, and so we've been calling that mult2. And if I was to write this polynomial as its linear factors, x minus 3 times x minus 3. And you can go ahead and FOIL that out, and when you do, you get x squared minus 6x plus 9. So this is what I mean by a polynomial. You can write it as linear factors, because when you multiply them out, you get your polynomial. And each zero is its own linear factor. A third degree polynomial has exactly 3 zeros. Third degree, 3 zeros. And in this case, we have x equals 0, x equals 2i, x equals negative 2i. So that would be x minus 0, x minus 2i, x minus a negative 2i is x plus 2i. And I want to point out that this complex roots, the 2i and the negative 2i, they come in pairs. So if you have one root that's complex, you're going to have another one. They have to come in pairs. Last one, fourth degree polynomial function has 4 zeros. So here we have x equals 1, x equals negative 1, x equals I, x equals negative I. That would be x minus 1, x plus 1, x minus I, x plus I. Again, the complex roots are in pairs. All right, we're going to confirm that the third degree polynomial function has exactly 3 zeros. And those zeros are x equals 0, x equals 2i, and x equals negative 2i. So here's how we're going to do this. We're going to take our zeros and we're going to write them into our polynomial. So f of x equals x minus 0, x minus 2i, x minus the negative 2i is x plus 2i. Let's go ahead and do some distributing. I'm going to go ahead and I'm just going to distribute those first. And I'm going to simplify. X minus 0 is just x. And then let's distribute. X times x is x squared. X times 2i is a 2ix. X minus 2i is a minus 2ix. And then I have a negative 2i plus a 2i. That gives me a 4i squared. And remember, I squared is the same thing as square root of negative 1. So I get x times, notice my 2ix and my negative 2ix, those drop out. So then I get an x squared. And remember from last time, I squared is the same thing as negative 1. So I get plus 4 times negative 1. Wait a minute, I got a mistake in here. Right here, I have a negative 2i times a positive 2i. So that's a negative 4i squared. So this is negative 4i squared. And that gives me x times x squared plus 4, and then do your last distribute, x cubed plus 4x. Boom. We've now confirmed that they're the same thing. Okay? Also notice that the complex numbers went in pairs. And what happened there is not only were they in pairs, but they were conjugates of each other. We had a positive 2i and a negative 2i, which then made your factors conjugates of each other. X minus 2i, x plus 2i. That forced your 2ix terms to drop out, so that got rid of the complex numbers in our polynomial. Okay, so that's why they have to come in pairs. I also want to point out that the x squared plus 4 that we got right here, that was a sum of two squares. Let me change colors. Let's erase this. Erase this. That's a sum of two squares. So the other day when we did difference of two squares, I told you that you couldn't factor a sum of two squares because it goes complex. Now we can use our complex knowledge and factor it. So if I need to factor a sum of two squares, so x squared plus, let's do 36. Let's just do something different. What I'm going to do, two sets of parentheses, x, square root your second term, 6, 6, 1 positive, 1 negative. So far this is just like difference of two squares. Now I have to put in the i's. Because remember, I squared is negative 1. It changes the sign on our last term. So that's how I get the plus for plus 36. So factoring sum of two squares, do the same thing as you do for difference of two squares. The only difference is throw in the i's right there and right there. Put your i's in. All right, now we're going to find the zeros of a polynomial function. We're going to find them as a product of linear factors, and then we're going to list all of those zeros. So what we're going to do first is we are going to try to find some real zeros. And we need to do that graphically on our calculator. So use calculator. So pause the video while you go get your calculator. So graph this on your calculator. So we're going to do x to the 5th plus x cubed plus 2x squared. Oops. Let's clear some of this off my calculator. equals x to the 5th plus x cubed plus 2x squared minus 12x plus 8. Now I'm going to graph that. And every time this graph touches the x-axis, I have a 0. So let's go ahead and find these zeros. One option is to open your table. So I have -2, 0, nope, that goes to 8. So I got -2 right here, and I have 1 right there. And that looks like it's also -2 and -1. And let's take a look back at the graph again. So -2 and 1. Look at that. I've got a bounce right here at 1. So I know that I have x equals -2, x equals 1, and there's a bounce. So I'm pretty sure I'm going to have at least 2 zeros at 1. So now what I'm going to do is divide these zeros out. Okay, get some zeros from your calculator, divide them out, and you need enough zeros that you can get down to a quadratic. So that means in this case, since I'm starting at x to the 5th, I need to remove 3 zeros. I have a bounce on 1. So I know I have at least 2 there, so I'm just going to do x equals 1 and x equals 1 again. So now using our synthetic division, let's start dividing out. So I have a -2 as a 0. So put in my columns, 1 for x to the 5th. I don't have any x to the 4th. 1 for x to the 3rd. 2 for x squared. -12 for x, and then 8. Bring that down. Let's divide this out. So I get a -2, add -2. -2 times -2 is 4. Add that, I get a 5. 5 times -2 is -10. Add, I get a -8. -8 times -2 is 16. Add, I get a 4. 4 times -2 is -8. I get a 0. Okay, I've divided one of these out. This is where that technique I showed you, where you can just stack your synthetic division as you go, comes in really, really, really handy. All right, now I'm doing this one. Bring down 1. 1 times 1 is 1. Add, I get a -1. -1 times 1 is -1. Add, I get 4. 4 times 1 is 4. Add, I get a -4. -4 times 1 is -4. Add, I get a 0. All right, that one's done. And one more of these ones to divide out. 1 times 1 is 1. I get a 0. 0 times 1 is 0. Add, I get a 4. 4 times 1 is 4. And I get a 0. So coming out of my synthetic division, I have x squared plus 4. Okay, now I need to solve that quadratic. Remember, difference of 2 squares and sum of 2 squared. X, 2, 2, plus, minus, put in your eyes. All right? So from here, I know I have a 0 at -2i and a 0 at +2i. And fundamental theorem of algebra says that I should have 5 zeros. So here's 1, here's 2, here's 3. X equals 2i is 4. X equals -2i is 5. So I've got 1, 2, 3, 4, 5 zeros. And then it says here to write it as the product of linear factors. So let's go ahead and finish up what it wants us to do. So f of x equals product of my linear factors. So I had a 0 at -2, so that's going to be x plus 2. I had 2 zeros at 1, so x minus 1 times x minus 1. I have a 0 at 2i, x minus 2i, and a 0 at -2i, so x plus 2i. That's my function in terms of 5 linear factors, and my zeros are -2, 1 with a multiplicity of 2, 2i, and -2i. And again, notice that those are conjugates of each other. All right, we are going to find a 4th degree polynomial with real coefficients that has -1 and -1 as zeros and 3i as a 0. So that means my linear factors are x plus 1 times x plus 1 times x minus 3i. This is 4th degree, so I need another linear factor. And my complex ones, they have to come in pairs. Must be pairs. So therefore, my other one is going to be x plus 3i. These come in pairs. Which means that my 4th 0 is going to be -3i, because it's the conjugate of positive 3i. All right, so let's go ahead and start distributing. I'm going to do those two first. So x squared plus 2x plus 1. When you FOIL that, that's what you get. This is a difference of, well, sum of 2 squares because we have the conjugates. So I'm going to get an x squared plus 9 out of that. So if you FOIL the first one, you get x squared plus 2x plus 1. FOIL your second one, you get x squared plus 9. And then we're just going to keep distributing. So let's distribute our first term, x to the 4th. Distribute second term, plus 9x squared. Now we're going to distribute the 2x. 2x times x squared is 2x cubed. 2x times 9 is 18x. Now distribute your last term, the 1, plus x squared plus 9. And that's what our polynomial is. Now let's see if we have any like terms we can combine. Also, let's put it in order from largest exponent to smallest. So x to the 4th, I have a 2x cubed. I have a 9x squared plus an x squared, so I get 10x squared. And I have an 18x and a 9. Done. It's 4th degree. All my coefficients are real numbers. All right, we're going to find another polynomial with the given zeros, a cubic polynomial. So cubic means it's going to be an x to the 3rd type polynomial. Again, real coefficients. It has 2 as a 0 and 1 minus I as a 0. So we are doing a cubic. That means we're going to have 3 factors. Okay. The first 0 is 2, so x minus 2. Second 0 is x minus 1 minus I. Now I need to get another one. And my 1 minus I has to come as a pair. You've got to use the conjugate. So my third 0 is going to be 1 plus I, because that's the conjugate. So this is x minus 1 plus I. Okay, let's distribute. And let's go ahead and take care of these. The x plus, can't talk, x minus 1 plus 1 minus I and x minus 1 plus I. And what I'm going to do is I'm going to treat this 1 minus I and this 1 plus I as its own term. And what I have here is a close to a perfect square. That's what I have here. So let's go ahead and start distributing. First term, x times x, so I get x squared. Second term, x times 1 plus I. Now distribute my 1 minus I. I get an x times 1 minus I. And then distribute the 1 minus I to the 1 plus I. So those are conjugates. You're going to get the sum of the squares of those. So I get a square of the first one is 1. Square of the second one is also 1. So I get a 2. And let's do some simplifying. X squared. I have an x plus I, as I distributed that, and I have an x minus I, x minus ix, and then I have a 2. All right, let's see what drops out. Well, my ix and negative ix drops out. So I get y equals x minus 2 times x squared plus 2x plus 2. And just keep on going, keep distributing. So y equals, distribute the first term, the x cubed plus 2x squared plus 2x. Now the second term, minus 2x squared minus 4x minus 4. So then y equals, let's see what drops out. Those drop out. So I get x cubed minus 2x minus 4. And we're done. All right, next thing we're going to do is we're going to factor this polynomial completely. And what we have here is x squared minus, x to the 4th minus x squared minus 20. And I'm going to do a technique that mathematicians often do, and that's called a change of variable. I'm going to make another variable, and this variable I'm going to call g. And I'm going to say that g equals x squared. And the reason I'm doing this is I can then rewrite this polynomial and we'll end up with a quadratic that we can easily factor. So f of x, or let's not even call it x anymore because I'm changing. So I'm just going to call this g squared, because g is x squared. X squared times x squared is x to the 4th, so g squared minus g minus 20. We're going to factor this. So I get a g and a g. Because I have a negative here, one is positive, one is negative. So I need a number, or two numbers, that multiply to negative 20 and add to negative 1. And I'm going to use negative 5 and positive 4. Okay, so that's my factoring. Now what I'm going to do is I'm going to go back to my original variable because I've got this factored. So I'm going to say x squared plus 4 times x squared minus 5. I have a sum of squares, which I can factor that now. X, 2, 2, 1 plus 1 minus, don't forget your I. So x plus 2i, x minus 2i, and x squared minus 5. I can then keep going And I can say x plus 2i, x minus 2i, and x squared minus 5, I can set that equal to 0. X squared equals 5. X equals plus or minus square root of 5. So now I've got two more linear factors. X minus square root of 5, x plus square root of 5. And now we're done. We got 4 factors, and this is a 4th degree. We're going to find all the zeros of this big and gnarly polynomial, given that 1 plus 3i is a 0. So that means that I have x equals 1 plus 3i. That's 1 0. So therefore, another 0 has to be the conjugate, so 1 minus 3i. Now at this point, you have 2 choices. Option 1 is to use long division. And you can actually FOIL your 2 zeros together, and then you'll get a quadratic and divide that out. Using long division, get another quadratic. Or option 2, calculator. The book does long division. This is the approach your book takes. Let's do it with our calculator, because that's going to be way faster. So grabbing our calculator, I'm going to graph this function, just like we did before, and I'm going to use that graph to get the real zeros. So I'm going to clear this out. We have x to the 4th minus 3x cubed plus 2x minus 60.